let's have another problem, including this chapter, the chapter gas power cycle under thermodynamics and heat transfer. For our problem, we have an ideal gas Otto cycle, and it's a compression of 8. And at the beginning of this compression process, air is at 100 kilopascal in pressure and temperature 70 degrees Celsius, and the heat of 800 kilojoules per kilogram is transferred to air during the constant volume heat addition process. Accounting for the variation of specific heats of air with temperature, let us determine the maximum temperature and pressure that occur during the cycle. So let's proceed. We're going to use our steam table since we are dealing with an Otto cycle and there is a variation of specific heats of air with temperature. Let us determine first our temperature. So our temperature here is 17 degrees Celsius plus 273 Kelvin. We acquire a 290 Kelvin temperature. So under that temperature, we have corresponding specific enthalpies, pressure, specific internal energy, and specific volume. Let's proceed. For our first process from state 1 to state 2, this is isentropic compression. So in this isentropic compression, we need to find for the specific volume at state 2. Since we already have our specific volume at our first stage, we need to find for our second stage at state 2. So this is the formula. And plugging in, we have now the 84.51 specific volume. This is at state 2. Next, after finding for the specific volume, we need to find for our second state pressure. What happened on the pressure on that second state, on that process? This is an isentropic compression. So we're going to use the combined ideal gas law, and by modifying and finding for our pressure 2, we acquire pressure 2 to be 1799.7 kilopascals. So that is the pressure under the process of the second state of this isentropic compression. For process 2 to 3, this is a constant volume heat addition. So when we say heat addition, there is a heat added into our system. So the heat is going in our system. So let us denote that it's a small letter Q. It is a specific heat input. It's equivalent to our specific internal energies at processes 2 to 3. So plugging in the given values, we locate or find for our specific internal energy at state 3, that is 1275.11 kilojoules per kilogram. At process 2 to 3, we also need to find for our pressure 3, that state. On this state, what is the pressure? So still using the combined ideal gas law, we acquire our pressure at state 3 to be 4.345 megapascals. Let's proceed to our process 3 to 4. This is isentropic expansion. For our isentropic expansion, we have an specific volume equivalent to our we have specific volume at state 4 to be 48.864. And moving on to our process 4 to 1, this is a constant volume heat rejection. After that cycle is compressing, constant volume heat addition. This time, after isentropic expansion, this time at process 4 to 1, we have a heat rejection under constant volume. When we say heat rejection, the heat on our system is going up. So this is denoted by Q out is equivalent to the difference between the specific internal energies of our processes 1 to 4 to 1. We have now our specific heat reduction to be 381.83 kilojoules per kilogram. Now solving for the work. We need to solve for the work, the network output of our ideal Otto cycle under this compression ratio and the constant volume heat addition process. So we have the work net is equivalent to the specific heat net is equivalent to the difference between the heat addition and the heat rejection. We now have our net work to be 418.17 kilojoules per kilogram. That is our net work output. For our thermal efficiency, the formula for thermal efficiency is equivalent to the work net all over the heat addition. So in this case, we now have our thermal efficiency to be 52.3%. While considering an ideal Otto cycle process, this is the efficiency that we're going to use. So using a ratio of 8 raised to compression ratio 1.4 minus 1, we have the thermal efficiency under an ideal Otto cycle process to be 56.5%. Solving for our mean effective pressure, that is denoted in this formula, we need the network input, we need the network output all over the specific volume minus the specific volume at state 2. So it's equivalent to the universal gas constant multiplied by our temperature over our pressure at state 1. We now acquire our specific volume at state 1, that is 0.8323 cubic meter per kilogram. For our mean effective pressure, the same, but in this case, our network is 418.17 kilojoules per kilogram. Plugging in the values needed, we now have our mean effective pressure. It is 574 kilopascals. Finding for our total mass. Determine the power output from the cycle in kilowatts for an engine speed of 4,000 revolutions per minute. So in this case, we have our network output, but this time using this mass multiplied to our network, we have a network to be 0.8037 kilojoules. And the total air mass using this specific volumes, accounting the variation of the specific volumes and specific heats, we have a total air mass under that cycle to be 0.001922 kilogram. So for our last question, we need to consider, or we have to find for the power output from the cycle in unit of kilowatts. So this time, an engine speed of 4,000 revolutions per minute. So we need to use our conversion skills in this process, since we are dealing with revolutions per minute and kilojoules per cycle for a cycle of ideal Otto cycle. For our network, we have 0.8037 kilojoules per cycle multiplied to the engine speed 4,000 revolutions per minute all over in 1 minute there is a 2 revolution multiplied to, let's convert our seconds into minutes, since it is necessary for us to revolutions per minute and the homogeneity of our units. So we have our network to be 26.8 in kilowatts. So that's all for our part 1 problem under gas power cycle of thermodynamics and heat transfer. So that's it, everyone. Thank you so much for listening. Thank you so much for supporting this video, and see you on our next upcoming videos to come. Have a good day.